So we're going to start again. The last thing we were talking about was the work energy theorem and the work done by a variable force. And we're going to use these two ideas to solve this problem right here. So let me zoom in just a little bit. Okay, so that's the problem we want to solve. We have a 4 kilogram block that compresses a spring. This is the spring constant by half a meter. So this is the equilibrium position. X equal to 0 is the equilibrium position right here. And we're compressing the block from that position over to half a meter. And it's released at rest. Our goal is to find the velocity of the spring when it's been compressed by 0.3 meters. So it'll start, right? The object is going to start from right here. So this would be kind of our initial coordinate. Maybe we call it x1 or something. And this is going to be our second coordinate. We'll call it x2. So x1 is going to be, I'm going to use a coordinate system so that x1 is going to be negative 0.5. And then x2 is going to be negative 0.3. Just making it, so that this is the positive x direction that way. So the block goes from here to here. And so we want to figure out the velocity that the block is going to have when it gets to this location, right? So it's going to have a velocity here, we'll call it v1, that's equal to 0. And then it's going to have a velocity here that we'll call v2, and that's what we want to find. The spring is going to push the block, and at this location it's going to have some speed that we'll call v2, and that's what we want to figure out. And we're going to do that under 3 different scenarios. 1, if the surface is frictionless, and then B, if the coefficient of kinetic friction is 0.1. Okay. So to do this problem, we're going to be using the work energy theorem. So we're going to be starting off by saying that whatever work is done by the spring, that should be equal to the change in the kinetic energy of our block. Now, we can fill out both sides of this. The work done by the spring is going to be given by this expression right here, right? It's going to be 1/2. It's going to be 1/2. It's negative k times x2 squared minus x1 squared. That's the work done by the spring. The change in kinetic energy is just given by 1/2 mass times the kind of the final velocity or the second velocity squared minus the initial velocity squared, like that. And we know that v1 is 0, so we can say here that this one is going to go to 0, and we can use that then to solve for v2, right? So then we would say the halves would cancel, right? And so we would say that the velocity 2, let's write it like this. We're going to have what we're going to solve for this. So we're going to have something like this. K divided by m, negative. And then we have our x2 squared minus x1 squared. And then we're solving for v2. So we want to take the square root of this. That should be what we get for v2. Did you guys understand what we just did? It's not very many steps. In very many ways, this is a lot simpler than using Newton's laws. Using work energy is almost always going to be quicker and easier. So then we just need to plug in our numbers. So K is 24 newtons per meter divided by the mass, which is 4 kilograms. There's the mass right there, 4 kilograms. And then this, there's a negative sign out here. This is multiplied by x2 squared, which was negative 0.5, so negative 0.5 meters. That's squared, and then minus, is there a question? No, I thought I saw someone typing. Negative 0.3 meters squared. And that should give us our velocity. 24 over 4 is 6. This minus this is going to be 0.4 squared, which is 0.16. I don't know what this is going to be equal to. Why don't you guys calculate it? Oh, I made a mistake, didn't I? I'm sorry, I'm being confusing. My bad. This one, the first one should have been x1 is 0.5, so this is 0.5 here. This is 0.3 here. My bad. I had those reversed. Yeah. Okay, why don't you guys calculate that and tell me what you get, or someone want to say if they get something. How did you get a negative sign? That's the right answer, though. It's about 0.98. So it's really close to 1, basically. So it's about something like that. What is it? Where do I round this off? We say 0.99, I guess, right? So it's like 0.99. Oh, I did a different color there. Whoops. How'd you get a negative sign, Vuv? VUV. It's going to the right, right? Oh, I'm sorry. It's tilde. No, you're good. That's good. I just, my second monitor, the text is a little smaller. Couldn't tell that was a tilde. Yeah, okay. Okay, does that make sense to you guys? The work done on the spring has the effect of increasing the speed of the object here so that it's moving a little bit faster. It was released from rest and now has a speed that's about 0.99 meters per second. So that's the answer for the first part. Okay, so that's part A. Okay, so part B, the only change is if the coefficient of friction is 0.1, right? That's what we want to, coefficient of kinetic friction is 0.1 acting on the object. So in that case, do a new problem here. So part B. Now what we're going to say, the one difference is going to be now we're going to have the work done by the spring. That's going to be the same as before. But we're also going to have to add to this the work that's done by the friction force. And then that should be equal to the change in kinetic energy for the object. Okay. So in order to talk about the work done by friction, this should be pretty simple for this problem. Let's go back up here. Just like say the forces that are acting on our object, right? There's a spring force that goes this way. There's a normal force that goes this way. There's a weight that goes down like this. And then the friction force is going to point back like that, right? And in this situation, we can say basically the normal force happens to be exactly equal to the weight. There's no other forces here, which means that the size of the friction force is just going to be equal to the coefficient of friction times the weight of the object. Right? So if we know that, then over here, we can talk about the work done by friction. So let's write down the work done by the spring again. So that's going to be, I got to scroll down just a little bit here because I don't want to write on the edge of the pad. So the work done by the spring is again going to be negative of 1/2 k times x2 squared minus x1 squared. And then to this we have to add the work done by friction. So the work done by friction is going to be the size of the friction force multiplied by the displacement, we'll just call it delta x. And then we also have to multiply by the fact that the friction force points opposite to the displacement, right? The friction force is this way, but the displacement is that way. So the angle between the two of them here is 180 degrees. So we have to multiply by the cosine of 180 degrees. And then all of this is equal to delta k, which is going to be basically just 1/2 m times v2 squared minus, and then v1 was 0, right? So we could start plugging some information in here. So the cosine 180 here is going to make this negative. The size of the friction force is basically just mu times the weight, which is the mass of the object times gravity. And we have to multiply by delta x. In this case, I'm going to say delta x is basically equal to x2 minus x1, right? So in this case, x2 was negative 0.3, I think. Whoops. 3 minus x1, which is negative 0.5. And I think this gives you 0.2, right? The delta sign basically means you take the second position minus the initial position, or final minus initial, whatever you want to call it. So all of this is times, I've defined what delta x is now, so I'm just going to put delta x right there. And that's all equal to 1/2 the mass of the object times the velocity that we're looking for, squared p2. Just a matter of rearranging here and multiplying through by 2 and then dividing by m. So we're going to get something like this. We're going to have negative k over m Does that algebra look okay to you guys? Does anyone have any questions? All I did here was I divided both sides by m and multiply by 2. There's a mistake then. This should be a 2 right here. Here, let me just make some more room. So it's 2 mu g. This should be a 2. Yeah, thank you. We can check units here too. The units of all of this stuff has to be meters per second squared. This is something that I highly recommend that you guys do when you're doing your homework problems. You should solve everything in terms of symbols, number one. You should plug everything at the end also. But you should also look at every term and make sure it has the right units. Okay, I'm going to do that real quick here on the side just so we can do it, so we can talk about it. Let's look at the units of this one right here. What are the units of mu? They're none, right? What are the units of gravity? It's meters over seconds squared, right? The units of delta x is going to be another meter, right? So you get meters squared over seconds squared. We're taking a square root. This one's good, right? Can you guys see that? This one's solid. This is definitely going to be the same units here as we have over here, right? Because we're square rooting everything. If we want to look at this one right here, it's a little more complicated because k, we said, was in units of... I need to scroll down to do this because I can't round the bottom of this. K, we said, was in units of basically newtons over meter. And we're dividing by kilograms, right? And then we're multiplying by meters squared, right? So what does this give us? Well, a newton is a kilogram times a meter per second squared. And we're dividing kilograms, right? And there's also this meter down here, so we divide by meter. And then we have times meter squared. And I think if you look at this, you're going to see that, the kgs cancel, these meters cancel, and again, you end up getting meters squared divided by seconds squared. So this thing becomes, again, meters squared over seconds squared. It checks out, right? And we're getting more square rooting, right? You guys should be doing this on every problem you do. And I'm sure that you probably won't because you're going to feel rushed and you're going to feel like you don't have time, etc. But I promise you by doing this on every problem, you will save yourself time by checking the units. So, all right. Did everyone follow what I just did? Do you guys have any questions about that? No as in you didn't follow, or no more questions? All good, okay. All right, so there we go. This is what we want to solve. I'll start plugging in the information. So I think k was equal to, so this is going to be square root of, I think k was 24 divided by the mass, which was 4 kilograms. All of this is negative. This is multiplied by x2. x2 was the one that was negative 0.3 minus x1, which is negative 0.5 minus 2. Mu is, I think, 0.1. We can go look. Coefficient of kinetic friction is 0.1. Yeah. And then obviously G is 9.8. And then delta X we said was up here with 0.2. All of that inside the square root equals V2. So then we get V2 is going to be equal to... When I finish this one, could you go back to the first version we solved, please? I got 1.4. Yeah, but we can put that in just a second, for sure. So this is going to be minus 2 times 0.1 times 9.8. So quick question before I look at the answer. Do we expect the answer to be bigger or smaller? When we add friction, and what's going to happen to the velocity? Is it going to get higher or small? Is it going to go up or is it going to go down? Yeah, it has to go up. It has to go down, right? Yeah, exactly. So what I got right here, yep, friction opposes motion, exactly. So another way you could say it is the friction is basically going to dissipate energy from the system. All right, so this is going to be 0.75, which is less, which is good, meters per second. That's what I got. And we'll go back and look at the last one. Okay, so any questions about this one real quick? Effectively, what this equation says, I kind of want to look at this equation right here in general, just to say something about it, right? What this equation says in words is this. It says that any work that's done by the spring, right, is going to give energy to this object, right? Even though there's a negative sign here, this quantity, there's a negative sign here, but this quantity inside of here was also negative, right? So this represents some positive number, right? That's the work done by the spring. We're subtracting from that. We have to subtract because friction is going to reduce how much energy we can get out of the system. So we subtract the work that's done by friction. And that's this right here. Okay. Now when we started, we said work done by the spring plus the work done by friction, but work done by friction was negative. And that work goes into the energy of the object, right? Work into energy. That's what that equation says, basically. All right, so yeah, you can look at this equation right here. You were asking Danielle Nicole about the how we got this answer right here. And for this, maybe I can I try to pull this calculator thing up again? Wait, is there a scientific? Oh, this is scientific. Okay. So we did the key thing, I guess, maybe here is that like because we're squaring. I don't know if this is clear, but because we're squaring these, the negative sign here doesn't matter, right? So let's see if we can plug this into this calculator here. I've got parentheses, it should work. So 24 over 4 is going to be 6. So we have negative 6. Whoops, clear. Oh, I just want to clear. Okay. So we have this one, I guess I push 6 and then negative. And then it's times open parenthesis. And then we basically just do 0.3 squared minus 0.5 squared, close parenthesis. Wait, why did it end up being negative? Shouldn't that give you a positive number? Just push equals again? Of course you do, because this thing is horrible. Okay. Anything designed by Microsoft is guaranteed to be hard to use. So that's how I get it. Does that, do you see what I did there? Danielle, did you get the same answer? And anyone else has a question, please feel free to ask in the chat. Oh, and then to get the final answer, yeah, you get 0.98, then we have to raise this to the 0.5 power, or it's just the same thing as taking a square root. And that's when we get the answer. This was the answer that we wanted, 0.9899. No, 0.98. It really should have been 0.98, right? I'm bad at rounding, sorry. My bad. It should really have been an 8 right here. Okay, so we erase this guy. That is 0.98, I'm sorry about that. Okay. So one more part to this problem. We now want to calculate if the friction coefficient is 0.1, how far will the block slide? That's what we want to figure out now. How far will the block slide? And the idea here is that if we compress the block, okay, maybe we draw a new picture for this part. So for part C, we have the initial position is we've got our so here's our surface. Let's say that this is the equilibrium position. And this was our initial coordinate, right? So x1 was equal to negative 0.5. And what we're going to look at is, suppose that we allow the spring to decompress to here, but then suppose that the block basically just slides, okay? And it comes to rest over here, okay? So the block slides between this point and this point, because the spring, basically, the way these springs work in physics problems, and I mean, this is kind of true with how springs work. Some springs work in real life, okay, but in physics problems, okay, and that's what you guys are gonna be doing, is solving physics problems. The way that these springs work is that if this object is like not actually attached to the spring, right here, right? The way I think about this, it's like a pinball machine, right? In a pinball machine, you pull back a spring, right? You let it go, and the ball shoots off, right? It's basically the same idea here. We compress something, and then we let the spring decompress, and then when the block gets to this location here, to here, when the block gets to like this location here, it basically detaches from the spring. Assuming that we're assuming that it's not physically attached, like it's not actually physically attached to the spring. It's just touching it, right? So the block is just touching the spring right here, and the spring pushes it away. Does that make sense to you guys? I'm probably over-explaining this. But the idea is then the block is going to slide through some distance. Call the distance d or something like that, right? And that's what we're looking to find, is how far is it going to slide? Okay. So what I'm going to do here is we're going to say that when we look at our equation for the spring, right, we had this equation that said the work done by a spring is equal to, we said that this was negative 1/2 k x2 squared minus x1 squared, right? And we're going to have the work done by friction, okay, which is going to be equal to, we could write this however we want to, but I'm going to write it like this. The block is going to slide from this point here all the way to this point here, so it will have gone this total distance, and we're saying this distance is 0.5 meters, right? So the work done by friction now is going to be mu times the weight, which was mg. It's going to be negative because of the cosine 180 that shows up. And now we're just going to multiply basically by 0.5 meters plus d on this one. That's just the distance the object slides, so that's going to be the work done by friction, okay? But the other thing I'm going to say is that when the object gets to this location here, right, the spring is no longer attached to it, right? So the spring is not actually doing anything. It's not compressed, it's not. So what I'm going to say is we're going to say that x sub 1 at this location is 0, okay? And the reason for that, and I'll explain just the different texts, is because the spring is at equilibrium, okay? And each of these distances, x2 and x1, they're not distances, they're coordinates. Each of these coordinates represents how much the spring is compressed, or how much the spring is stretched. So in this case, if the spring decompresses to here and the block starts to slide, the spring's not doing anything. So that's why I'm saying that, yeah, this little piece right here is going to be 0. So when we write down our work is equal to the change in kinetic energy equation, it's going to look pretty similar to before, but now we're going to have a couple other things here. First of all, I left another thing out right here we need to indicate as well. Within the kinetic energy, of course, is, you know, the initial and final velocity, right? So this has within it 1/2 mass times v2 squared minus v1 squared. So we also need these pieces of information, right? So this would be v1, And then this would be v2 over here, right? Can you guys tell me what's v1 equal to? You just cue your mic and say quickly. What's the initial velocity of this object equal to? Zero, right? Because it was released from rest. What's its velocity going to be over here? Oh, I already wrote it down. This is also going to be zero, right? Its initial velocity and its final velocity are going to be zero, right? So in our equation now, basically this one, 0. This one, 0. So all we have is basically just the work done by the spring plus the work done by friction is going to be equal to 0. And we've got those guys over here, right? So we can write that out. That's going to become, negative 1/2 k times, oh shoot, I am sorry. This is x1. This is x2. Its final position is going to be x of 2, my bad. So then over here, it's that one. Sorry, the final position that's 0. Sorry for being confusing. Kind of like lost in the work as I'm writing. I'm not stepping back to see what I'm doing. I'll stop for a second so you guys can fix your notes and stuff. Everybody okay with that? So final x coordinate is going to be 0 for the spring, v2 is going to be 0, and then v1 is 0 and x1 is 0.5. Okay, so what we end up getting is this. The work done by the spring becomes negative 1/2 k times negative, so you just get, you get this times k times x1 squared. Okay, and then minus this guy. And then we just solve for d, right? Okay, I'm going to write this in a little bit different way than I just did. Let's write it like this. I'll let you guys solve for d here if you want to, but I think it's going to be equal to something like this. We're going to get k x1 squared. We add this thing to the right-hand side of the equation, and that's going to give us, we're going to be dividing by mu times mg, and then we're going to subtract 0.5, and that should be equal to the distance. You can work out the algebra for yourself if you want to there. Just isolate d. I think this is what you're going to get. So I think k was 24 newtons per meter. X1 was negative 0.5 meters squared. Mu is 0.1. The mass was 4 kilograms. And obviously gravity is 9.8 meters per second squared. G is always positive in these problems. It's not because G's positive, it's just the quantity G is always represented by positive 9.8, and then we subtract 0.5. And that gives us the distance. I didn't try to do this on this calculator. It's not that bad, I guess. All right, so let's just make this so I can see what we're doing. So, okay, clear. So we're doing 24, get 1.03 meters. That sounds right to me. So it's 24 times 0.5 times 0.5 divided by 0.1 divided by 4 divided by 9.8. That'll equal something, and then 1.03. That looks like the right answer because you'd subtract off a half. So this is going to give you 1.03 meters. And we can check the units. It should work out that this gives you meters here, hopefully. That's the distance that it's going to slide. That would be to the right of the equilibrium position. Okay. Total distance would be 1.53 meters from where I started. Anyway, so that's it. Go ahead. Oops. Yep, there it is. Right there, there's the 2. I had it written and then I erased it. Thanks. There's supposed to be a 2 there, which means our answer is going to be wrong. Thanks for catching that. Appreciate that. Oops. Erase. Oh, that's weird. If I go... Oh, because I need to do this and this? I don't know. Okay, what do you guys get then if you fix that? It would basically be this divided by 2, right? And then minus 0.5. 0.26. It's really 265. Is that what you guys got? 0.27. Yeah, there you go. Cool. Thanks for catching the mistakes. Why is the no hole? What happened to learn negative in the equation? Oh, I mean, just solve this equation. Solve this equation for D. This is what you're going to get. Oh, the negative 1/2. Sorry, it's from here. Negative, negative. That's why it's positive now. Kind of skip that step. All right. You guys have other questions? Hopefully that made sense. Personally, I think doing problems using energy is easier. I think that it's a little weird at first when you're learning this stuff, but you eventually figure it out, hopefully. Okay. Getting through this stuff way faster than I thought we would. Because we only really done 2 problems, but still. All right, so yeah, let's start talking about other things. The next thing we need to discuss is forces. So conservative and non-conservative forces. This is what we want to talk about now. If you've taken some math classes, then you may have talked about conservative and non-conservative fields. Have you guys ever heard that expression before in your math class? Conservative fields? Talking about vector fields maybe or something like that? Okay, this is basically the same concept. So let's start with non-conservative because I think that to some extent they're the more natural one to understand. So a non-conservative force, I'll use NC for this, okay? So a non-conservative force this is the definition of what it is. It's a force when you calculate the work done, it depends on the path. So this is the work done. Give you a very simple example of this. Suppose that we have a table, okay? So I've got some surface right here. And on this surface, I've got an object, okay? So I've got like a box that I'm going to move around the surface, okay? So I've got some box right here, some mass M. And let's say that I want to take this box and I want to move it between, let's say, this point where it starts right here, which we call A, and we want to move to another point over here, which we call C, okay? And we look at the different paths that we could take to move the object there. And let's say that on this surface, that the only force that this block is subject to is friction, okay? It has gravity pointing downwards into the board. Sorry, downwards. Gravity in this picture is going to point into the screen, and the normal force would point out of the screen. So you just have a tabletop, right? And this box, as you move it around the table, it's going to feel forces of friction, okay? So there is friction on this surface of some kind. Now, if I want to calculate the work done by friction, okay? Suppose that I take the object and I move it along 2 different paths, okay? So let's say that one path that I have it travel along is straight like this, okay? We call that one path 1. We even call it maybe path AC. And then we think about another possible path, which I'll do in green. And that path could be that you go over to here first, okay? So the other path could be that you go this direction, and then you go this direction, okay? All right. So the work done by friction is going to be different depending on which path you choose, right? Can you guys tell me which path is going to have more friction? Is it going to be path AC or path ABC? Yeah, it's pretty obvious, I hope, that along path ABC, because the distance is larger, the work done by friction is going to be larger, okay? Now with friction, it's pretty simple. The longer the path, the more work you have done, right? It's that simple, right? So does that make sense? That's really what a non-conservative force is. Okay, it's a force where that happens, where there's more work done depending on the path that you choose. Okay. Does anyone have any questions about that? Hopefully that should make sense to you, right? It should be pretty intuitive that if you push the box for longer on the surface, friction's going to do more work, right? Okay. Now, there's other types of forces that are called conservative forces, okay? And a conservative force, you can pretty much guess what it would be. It would be a force where the work does not depend on the path, okay? So a conservative force is defined as one that does the work done by the force does not depend on the path, okay? So a conservative force the work done only depends on the endpoints of the path. So I'll give you an example of this one. So let's say that this is the ground, okay? Gravity goes this way now. So gravity points down, right? And I want to consider two different paths. So we'll take an object that goes, like, let's say from point A, and we'll move it to point C again. And we'll put our point B right here as well. And we'll calculate the work done along these paths. And to do this, we're going to need a little path to describe here, and then we'll need another path to describe below it. Okay, so these are our two paths. Okay, and just for simplicity, so I don't have to use a lot of letters, we'll call this path 1, and we'll call this one path 2. And we want to find the work done along those paths. Now, we need some distances in here to actually do some calculations, so let's label some distances here. Let's call the distance from A to C, we'll call that one S. And we'll also define this angle that's made right here, we'll call it theta. All right. And we need something to move to, right? So let's get an object. So we got like a ball, and let's say it has a mass m. Okay, so the ball moves along our paths right here. The ball at different points in the path so we can draw forces and stuff like that, right? Okay, let's talk about path 1 first. We take a ball, we move it from point A to point C, okay? We could be pushing it up a ramp. We could be just taking the ball and just like dragging it in space. Like we can pick it up and just move it along this line. Whatever we're gonna do. This is the path that it takes in space. Okay, we don't really care what is going on. It's just that's the path it takes through space is along this thing S right here, okay? The direction of the force of gravity acting on this object would be downwards, right? That's the force of gravity. Same thing here. The force of gravity acts down. Okay. The path, okay, let's use a different color for that. Maybe blue or something. The path vector points this way, right? Yeah. Call it, I don't know, S or something like this, right? It's a vector now. And now we can say that the work that's done by the force of gravity, this would be path 1, the work done by gravity should be equal to the force of gravity, which is mg, multiplied by the path length, which we called s, right? And then we also have to multiply by the cosine of an angle. And in this case, that angle is going to be the angle between, here and here. So if this is theta down here, then I think it's going to be the cosine, whoops. So it's going to be mg times s times the cosine of, I would say, 90 plus theta. Does that look right to you guys? You take the force, you multiply by the displacement, and then you multiply by the cosine of the angle between the two of them, which in this case should be 90 plus theta. Everyone okay with that? All right. Now, we do the same thing on the other path, okay? On the other path, the force of gravity also points down, right? Along AB, so let's look at path 2 now. What's the work going to be done on the object from A to B? Can anyone tell me what it is before I calculate it? Between these 2 points, what's the work done by gravity going to be if this line is level with the ground? You keyed your mic, but you didn't say anything. Did you say 0? It's going to be 0, that's right. So it's going to be basically mg multiplied by this length down here now, which if this is s, then the length on the bottom should be basically s times the cosine of theta, right? That's how long this side is here, right? Is s cos theta. So it's going to be mg times s times the cosine of the angle theta. That's the displacement. Okay, this right here is just the distance, or the displacement that it moves. In addition, you also have to multiply by the cosine of the angle between the two vectors, between FG and your displacement vector, which in this case is 90 degrees. So along AB, the work done is 0. Okay? Hopefully everybody follows that. Along BC, though, okay, now the direction of the force is down. Oops. That's the force of gravity now. And our path vector goes this way, right? So the angle between these two guys is going to be 180 degrees, which means that on BC, what we're going to have is the work done by gravity is going to be equal to mg times the displacement, which in this case is going to be the length of this side. And I'm going to say that the length of this side, the length of this side is going to be s times the sine of theta. That's how long that side is going to be. So it's going to be mg times s times the sine of theta. And that's our distance. And then we have to multiply by cosine of 180. Okay? So what we're ultimately going to get here basically is just negative mgs times the sine of the angle theta. That's the work done along the other path, okay? So this is our answer to this part. That was our answer to the first part. I believe that there is an identity that states that if I take the cosine of 90 plus theta, that this is equal to the negative sine of theta. I'm pretty sure that's an identity that exists out there. So that means that this one is equal to negative mgs sine of theta. Does that identity look okay to you guys? If someone can verify, you can try some numbers if you want to. Just plug some numbers in there and see if it works. Pretty sure it works. Because if I have a coordinate system and I have some angle theta right here, then 90 plus theta is going to be an angle this. And the cosine of that angle is definitely negative, number one, okay? But in addition, the angle that you'd be talking about there, since it's 90 plus theta, it's going to be related to the sine, because you're shifting by 90 degrees. And the negative sign just comes from the fact that it shows up in the second quadrant. So the thing to look at here then is that you get the same answer here and here, which means that the work done by gravity is path independent. Here it is, path independent. You get the same answer no matter how you do it. And the main reason is because when I take an object and I want to move it from A to B, it takes no work to move it laterally. It only takes work to move it upwards. That's the key thing to understand. You only have to do work against gravity when you change elevation, right? It's not that hard to walk on a level surface or to run on a level surface. You won't get tired. But if you try running uphill, you'll start to get tired very quickly because you're doing work against gravity, right? And technically, even when you're going downhill, running downhill, you're still doing work against gravity, right? If you're riding a bike, the bike can use the motion of the wheels to like basically carry you down the hill. But if you're running, it's a little different story, right? Because you kind of have to, you don't want to run down the hill too fast. You don't want to roll down the hill. Anyway, the point is you only do work against gravity when you change elevation. Does that make sense? So it's only the y coordinate that actually matters. If you look at what we got here, right? We defined S to be this vector that goes basically from here to here. And we found that it was only the y component that shows up, right? S sine theta, S sine theta. That's the y component, right? So ultimately what this means is that all you care about is how high the initial point is and how high the final point is. And then the difference between those is going to tell you something about the work done by gravity. And we'll develop that more explicitly here. I just want to prove that with gravity, the path you take doesn't matter. And the path could be curvy too, right? So the path could be something like, you know, you could start at some location and then you could go up this way and then that way and this way and that way. It doesn't really matter. All you care about is the initial y coordinate and then the final y coordinate over here. That change, that elevation change, is the only thing that's going to be relevant in terms of gravity. Is this delta y right here. Does this make sense to you guys? Does anyone have any questions? All right. What I want to do now then is to develop for conservative forces in particular. There is something we can write down called the potential energy. For conservative forces, there's always a potential energy, okay? And the way that we define it is kind of like this. I'm noticing that it's 3:45. That's probably a good time to take a break, actually, for 10 minutes. And we'll talk about potential energy when we get back, okay? So we'll say take a break, and I'll just stop the stream now.